Hey, the first video we're going to look at is the 2018 free response question, and this is number 1. Okay, so let's read through the problem first, and then we'll kind of discuss what it's already given. Now, the use of a calculator is required, so we'll get to that here in a second. But people enter a line for an escalator at a rate modeled by the function r, given by r of t equals 44 times t over 100 cubed, times 1 minus t over 300 raised to the 7th, but that's only good for t between 0 and 300, and then the equation equals 0 for t greater than 300, where r of t is measured in people per second and t is measured in seconds. As people get on the escalator, they exit the line at a constant rate of 0.7 person per second, and there are 20 people in line at time t equals 0. Looks like we have 4 different pieces to this puzzle to solve. The first thing that I would do, though, is because there is an equation in this opening stem, what I would do is I would go ahead and put that into y1. Okay, that's the first thing I would do. Because we'll probably end up using this equation throughout this problem, I would go ahead and type that in. Okay. Remember, you can type in a fraction by pressing alpha y equals and using number 1 here. It's pretty handy and good to know. Okay, so let's go ahead and get started on part A. How many people enter the line for the escalator during the time interval 0 to 300? Okay, people enter the line based on the equation of r of t. It says people enter a line for an escalator modeled by the function r. Okay, so part A, what we'll do is we're just going to take the integral from 0 to 300 of r of t dt. And this will represent the total accumulation of people entering the line from 0 to 300. So for this one, we'll just use our calculator. So we'll go math 9, okay, F-N-I-N-T, but math 9, and then it's from 0 to 300. And then we're going to use y1, and then for dx. Okay, now I realize that the variables in my problem that I'm writing on my paper don't match up to the ones on the calculator, but as long as you're staying consistent, the ones on your paper should match and the ones on your calculator should match. Okay, so these are good because they're both in terms of x, and the ones on my paper are good because they're both in terms of t. Okay, all right, so let's see what we get here. 270. So according to this equation, there are 270 people. So 270 people enter the line from t equals 0 to t equals 300. Okay? 2 points for that one, 1 point for the integral, 1 point for your answer. Okay, so let's take a look at part B. During the time interval from 0 to 300, there are always people in line for the escalator. How many people are in line at time t equal 300? So what we're going to do for part B is we're going to look at the total amount of people on this line. And what I like to do for the problems like these is write an equation. So we're going to call this L of t. L of t will represent the amount of people on the line. Okay, and so when we're looking at an equation like this, we want to start with my initial number of people on the line, and it tells me that at time t equals 0, there are 20 people in line at the time. Okay, so that's my initial. And then we're going to add on the net change of people. All right, so we're going to go from 0 to t, and we're going to look at the net change. So the people entering the line, people enter the line at the equation r of t, which we have typed in our calculator, and then people exit the line at a rate of 0.7. All right, if we go back and read the problem again, it says as people get on the escalator, they exit the line at a constant rate of 0.7 person per second. Okay, so that's the 0.7 seconds, or 0.7 people exiting the line. And we're going to call this, we can't use t here, so let's call this r of x. Okay, and so people entering and people exiting. People entering would be a positive rate, and people exiting would be the negative rate because we're subtracting those people that are exiting the line. Okay, so this is the entering rate. This is the rate leaving. All right, and then I want to know how many people are in line at time t equals 300. So let's just go ahead and plug in 300. So 20 plus the integral from 0 to 300, r of x minus 0.7 dx. Okay, so let's type this in the calculator. 20 plus math 9, 0 to 300. y1 is my r of x equation, minus 0.7, and then dx is 80. So at time t equals 300, there are 80 people in line. Okay? All right. Now for part C. Part C says, for t greater than 300, what is the first time t that there are no people in line for the escalator? So I want to know when there are no people. And this is for t greater than 300. Okay? All right, so we can use the same equation we had here before, or something very similar to it. We still need to look at how many people were initially on the escalator at t equals 300. We want to know the rate at which they're entering and the rate at which they are leaving. So we can call this a different equation because this one is for people, or for time greater than 300. So we'll call it m of t. For time greater than 300, at 300, there are 80 people, and we just found this out from part B. Okay, so 80 people plus the net change of people entering and exiting from 300 to any given time t. So if we look at our equations here, the original model given for r of t, for t greater than 300, there's no one entering. Okay, so we'll include that for now, but as we progress through the problem, we may end up dropping that 300. So the 0 represents the people entering minus the people exiting. So people are still exiting at the same rate. That rate has not changed. So this would be minus 0.7. And we'll call this dx because, remember, the variables in the integral can't match the variables at the end. Okay? Okay. So I want to know when there are no people. If this equation represents the total number of people on the escalator for time greater than 300, if there are no people, then that means that this would equal 0. And at this point, 0 minus 0.7, I would just put it as minus 0.7. Okay? And let's go through and solve this equation. So 0 equals 80 plus, remember, to evaluate an integral, you have to do an antiderivative. So we are doing the antiderivative of this equation, negative 0.7 with regards to x. So I'm going to use negative 0.7. Remember, you just add on a variable. So x evaluated from 300 to t. Okay. Now we plug in the top bound minus plug in the bottom bound. Okay. If you need your calculator, you can use your calculator on this one. You may or may not. Let's see here. 0.7 times 300. It's 210, so 80 plus negative 0.7t plus 210 equals 0. Let's solve this equation for t. Add the 0.7 to the other side. Equals 290. So take 290 and divide by 0.7 and get 414. So at time t equals 414.285 seconds, there are no more people in the line. Okay? All right, part D. For t between 0 and 300, at what time t is the number of people in line a minimum? To the nearest whole number, find the number of people in line at this time. Justify your answer. Okay, so if I want to find a minimum on a closed interval, I should be thinking through candidate test. All right? And the candidate test will count as all my points for the justifying your answer. Okay, so let's start the work for this one. So let's talk about the equation that represents the people in line. We are talking about from 0 to 300. So we can go back to a previous equation here. And the equation that I was able to write that represented the number of people on the line, we wrote that in part B. That is the number of people in line at any given time for t greater than 300, or for t between 0 and 300, I'm sorry. Okay, so if I'm thinking through, I've got a closed interval, I want to find a minimum, then this is candidate test, like I said. To do a candidate test, we need to figure out the derivative and set it equal to 0 or undefined. In this case, it's just going to be 0. Okay, so let's find the derivative. The derivative of this, the derivative of 20 is 0. So let's do the derivative of the integral now. When you do the derivative of an integral, you just plug in the variable bound. So I'd have r of t minus 0.7. That is the derivative. And what we're going to do is we are going to figure out when this is equal to 0. So on my calculator, I'm going to make a new equation in y2, r of t, so that's y1, minus 0.7. And when I view this, I don't want to look at y1. I am going to change my window though. Because I'm looking for something between 0 and 300, I'm going to make it negative 10 to 300. It doesn't matter what your negative value is. The scale, we can go by 50s. The y min and y max, it really doesn't matter for the minimum or maximum on the y-axis because I'm concerned with finding zeros. Okay, so let's see what this graph looks like. Okay, it looks like it's equal to 0 in two different places. Those two places being here and here. So let's go ahead and find those. So remember, to find a 0, we go second trace, number 2, which is 0. And we need to be on the left side and the right side. So I'm going to go on the left side, I'm going to go on the right side, and I find that intersection at 33.013298. Now, if I go back to the home screen by pressing second mode, second quit, the x value that's currently stored is that number, which is pretty handy. Now, we saw that on my graph I have two different points where there's a 0, so I want to call one of them A and one of them B. So I'm going to store this value as A. Okay, so now no matter what I do, whenever I type in the variable A, I will get that number. So the first answer here was 33, whoops. And I'm going to list them all out on my paper. 0.1329,783. And then this will equal A. Okay, and I'm doing this as kind of like a note to myself. Whenever I use the letter A, I know that it'll be there. And then let's find the other 0. Okay, so same idea, second trace, go to 0. Be on the right side, be on the left side, and this 0 is 166.57472, and we'll call this one B. Okay, again, the x value has been replaced by this new intersection, or by this new 0, but I want to call this B, so I'm going to store this as B. Okay, so we figured out the critical numbers. Remember, these are what we call critical numbers. So now that I have my critical numbers, I'm going to test all my candidates, which are my endpoints and my critical numbers. So make my chart, and it's going to be 0, A, B, and then 300. Okay, the 2 endpoints and the 2 critical numbers that I found. And what I'm going to do is I'm going to plug these into L of t. Okay. So we can use that same equation. Some of these we already found. Some of them we're going to need to find. For the sake of the problem, I'm just going to show you how to type them all in. So 20 plus the integral from 0. And this one goes from 0 to 0 of r of t minus 0.7 and then dx. So I got 20, which is good because it told me in the beginning of the problem that at time t equals 0, there were 20 people in the line. If I got a number that was different, then I may want to check that because I may have done something wrong. I can go up and copy the same equation, except this time, instead of 0 at the top, I'm going to put an A. So 3.803. And then I'm going to do the same thing, and I'm going to put in B at the top. And this time I have 158.070. And then I can do the same thing just to verify this. Now we should get the same answer as we got somewhere else, but from 0 to 300, this was 80. Okay? So I want to know when there's a minimum. There is a minimum. The lowest value, the smallest value is this 3.803. So there is a minimum at time t equals 33.013 seconds when there are. Now this problem says to round to the nearest whole number, so the nearest whole number here would be 4. Okay. I know I may have talked about this in the beginning, but again, remember the free response problems are worth 9 points. 1 point, or for part A, there's 2 points, 1 point for your integral, 1 point for your answer. In part B, it's worth 2 points, 1 point for considering the rate out, and then 1 point for my answer of 80. In part C, this is just 1 point for the 414. In part D, we need to consider this equation. We need to identify 33. We need to have my answer and then my justification, which the justification here would be the candidate test. Okay? Okay. That's it for this one.